The next test is on Tuesday of next week. It'll be on Chapter 13, and however much of Chapter 7 we get done by the end of next class. So James was talking about the way I write my 8s. So here's my explanation for that. So when I took mechanical drawing in college as an engineer, they taught you how to draw letters, the numbers. So here's my numbers. So a 1, you always do a little thing like that, and then a cross like that. Okay. So that's 1, and a 2 looks like that. A 3 looks pretty much like a normal 3. A 4 always was like that. 5, that was pretty standard. So with a 6. And when you did a 7, you put a little cross like that. That was to make it look different than some other letter or number. And then here's the infamous 8s. So an 8 would look like you would draw 2 circles like that.
How do you draw the infinity sign?
I'll do that in a second. And then, yeah, so that, and then the 9 would be, you'd actually, I think I remember you actually did, I'm not sure if you drew it, little curl. I just draw them straight. So that's my 8. You do 2 circles like that. Except nowadays I tend to draw them too fast and you don't quite see them. The infinity sign, yeah, I actually do that. Yeah, so you're saying you'd do it. See, you notice how I do. If I do it that way, I do it at an angle. I can't even do it anymore. It's like that. Yeah. So yes, I do an infinity with 2 circles. Yeah. Anyway, I can't do it anymore. Okay, onward with, we were doing section 2, but I had all this in one file, so there we go. So we did a mixture problem. That was the last thing we did. Again, remember the test is next Tuesday on chapters 13 and 7. Pardon me? Yes. Mm-hmm. Yeah, did I ever tell you when the final was? Okay, let's look at that. I have to get the final schedule up. Equations and substituted in the second 2 equations into the first equation to get an algebraic equation in one variable. And the last kind of example problem is this one right here. And so this is 45. John Allen earned $12,000 last year by giving tennis lessons. He invested part in 3% simple interest and the rest in 4% interest. He earned a total of $440 in interest. How much did he invest at each rate? Those are the answers, but let's see how we get to the answers. So it's kind of like the mixture problem in some sense, because we have this column, which is the amount of money he has, and there's going to be an amount invested at the lower rate and the amount invested at the higher rate. This is the one, this column will give me the equation that I will solve for the unknown. So we have, instead of percent solutions, we have percent interest. Instead of liters of solution, we have principal, and instead of liters of the acid, we have that. So, but it's a similar types table. So we have to decide what is the variable, and it says how much do they invest at each rate. So you might be tempted to say, okay, I'm gonna say the amount that's invested at 3% is X, and the amount invested at Y, the amount invested at 4% is Y. And then you can calculate the interest by multiplying the interest rate times the principal to get the amount of interest. And we could do that. There's actually an easier way, because if I assign the variable X to the principal for the 3% and the total is 12,000, then what is the amount of money in terms of these two numbers that are invested at 4%? So what number, what would I put in here? Tucker, what do you think? So if I have 12,000 total dollars, would you say something? So if I have $12,000 to invest, and I'm investing X at this percent, then how much do I have in terms of these two variables? Let me ask you a question. If I said I'm going to invest $5,000 at this interest rate, and I'm investing $12,000, how much do I invest here? So there's 5,000 here, there's 12,000 there. What does that have to be? This is 5 plus something equals 12. 7,000, exactly. Okay. So that would be in terms of if I pick X. But if I don't know X, whatever X is, this one has to be 12,000 minus X. Okay? So that's how these problems work. When they give you the final amount, and you're trying to figure out each individual amount, then you assign X to one of the values unknown, and the other one has to be the total minus the other part. It's kind of like, there's a lot of problems we do in calculus where maybe there's a distance, and let's say this distance here is 3 meters, and if I pick, and then that 3 meters was made up of two parts, two subparts that add up to 3. Shh, don't be disruptive. So if this is X, then this has to be 3 minus X. So we don't necessarily have to, the other way you can think of it is you could say it's Y, but Y would have to be, you know, you'd say Y is equal to 3 minus X for the thing to work out. Okay. So once you have that part done, you can calculate the third column. So the amount of interest on X principal at 3% is just going to be 0.03 times X. And the amount of interest at 4% is going to be 12,000. It's 4% in decimal form times 12,000 minus X. And the total amount of interest in 1 year is just going to be the sum of the interest for each account. So let's so our final equation results from just adding the numbers in the third column. So you get 0.03 times X plus 0.04 times 12,000 minus X equals 440. So now we have a single equation in a single variable. So go ahead and solve that. Remember what we do. When you have decimals, you multiply by the multiple of 10 that gets rid of the decimals, and you apply that to every term in the expression. So go ahead and multiply that out by some number. And then you'll get the equation just in terms of integers. And then once it's in terms of integers, it should be easy to solve. And then when you get the answer, you know, you think about, does it make sense or not? One way to think about it in this case is if it was all at 3%, you would get 0.03 times 12,000, which would be $360. And if I do it at the higher interest rate, it'd have 12,000 times 0.04, which would be 480. So you got 480 on one bound and 360, and the one we're looking for is 440. So it seems like you should have more money in the higher rate than the lower rate, just based on the kind of the limits. So if you guys online, if you can put me an answer out there, please. That's a multiplication, not a decimal, so that one. You got a mechanical pencil failure back there? I was telling my other class a story about my daughter. This is one we visited this weekend in New York. She's talking about her experience buying a car. She bought a Toyota Prius a couple of weeks ago. And they did the loan through Toyota because they had a special, 3 years, 0% interest or something like that. She had to give them her salary and her husband's salary. Well, she makes more than her husband. And the salesman said to her, well, we see who wears the pants in this family. He did. So she didn't slap him, but she wanted to, I think. And then he made some comment about the car had some kind of plug-in thing for appliances, and he said, "Oh, you could plug your hair straightener out in here while you're driving to work. You work on your hair." She says, "Well, I do not do that in my car," or something. I don't know. She said they were. Oh, what's that? Yeah, well, they'd already bought the car, I guess, and she put up with it. But yeah, that was not very inappropriate. Okay, so we combine like terms. So we get 48,000. See, there's my 8 again. 48,000 minus x equals 44,000. We add the additive inverse of 48,000 to get the other term to the other side. So that leaves us with negative x equals negative 4,000, or x equals 4,000. So what we would say, and you might stop there, but you got to read the original question. How much did he invest at each rate? So $4,000. So the answer is $4,000 at 3% and 8,000, which is from here. So 12,000, x is 4,000. 12,000 minus 4,000 is 8,000. So you'd have 8,000 at 4%. And that would be the answer. So be careful of that. So this is interesting. My wife is she saves money through school, and she was trying to figure, they sent her statement, and it said this is how much money you would get if you purchase a annuity, and the annuity would last for your lifetime. So I thought I'd tell you about annuities. This goes back to chapter 13. So Social Security is kind of like an annuity in that you put money in while you're working, and then there's this amount in there. But everybody, not everybody lives to be 100, but you still get paid Social Security until you're 100. It's not going to run out, or at least theoretically shouldn't run out. Now, if you only live 5 years after retirement, then you don't get as much money as the person who lives to 100, but you get it for your life. So that's the important thing. The only good money is when you're dead is to give it to your kids. So it's the advantage. And you can do the same thing with annuities. You can buy annuities which are for like 20 years, and it'll give you money for 20 years, and then it runs out. Or you can pay a little more for an annuity, and it'll cover the person for their lifespan. So again, if you could take that cash and just give it to your kids or something like that, or you can put it in an annuity, which kind of gives you a guaranteed income for your lifetime. And as a consequence, you get less money if you died early than if you died later. So it's kind of it's not gambling. Maybe it is kind of gambling. You're gambling on how long you're going to live, and the winner is not you because you're dead. The winner is your kids, depending on what you get. But if you live too long, you're the loser if you buy an annuity or you do something with a fixed time span to it. So I thought of our discussions of. But the interesting thing was I used a spreadsheet to figure out what kind of interest you were getting on that money as they were paying you out of it. Even if you live to be 100, what your interest would be. And it wasn't that tremendous. It was not impressive. It was maybe like 2.5%. And if they invested all that money as a company in the stock market, and they got 11%, and they're only having to pay out 2% to you, they're making a lot of money. The question is, do you invest in the stock market as a company because the stock market could go and then you wouldn't have any money to pay anybody, and that's I've seen things where they'll pay you, they talk about 4 or 6%, and so that was pretty pathetic as far as I'm concerned. Okay, so we're going to do a couple here where we have to come up with the equation based on the words. So these are just single variable equations. So see if you can come up with an equation. Remember the different words for plus added. So we're going to take 2 plus 5 times the number. So when you see a number, and it's only a single number, that means you can always count that as you can say the number's x. So you can substitute the words a number with the letter x, or whatever letter you want to use. The result is equal to, well, that's an equal sign. 5 times 5 more is going to be add. 5 more than 4 times the number. Okay, so see if you can come up with the equation. I'll give you a minute to do it. And then it says find the number. So once you get the equation, that's pretty easy. It's just single. The hard part is coming up with the equation. Did anybody ever give me a number from the, did they give me, 4,000, yep, very good. You are paying attention. So I'll give you another 10 seconds. So you get 2. The question is where do you put this? 2 is added to 5 times the number, so I would tend to do 5 times the number, and 2 is added to it. But you could have 2 before. It doesn't matter. The order of addition doesn't matter. The result is equal to 5 more than 4 times the number. So that would be the equation you should get out of that. Now you can solve it by isolating the variable terms on one side by taking the additive inverse of one of these variable expressions, which I choose this one because I can solve for x over here, and taking the additive inverse of this number and do that to both sides. And then I do the addition, so I got 5x minus plus a negative 4x, which is just 1x. This goes to 0, this goes to 0, and we get x equals 3. So the answer is x equals 3. Okay, let's do another one here. No, this is a different one. Motion problems, yeah. So we've done mixture problems, we've done money problems, we're going to do motion problems. That's the last kind of problem that we're going to do. And the key thing about motion problems, for mixture problems, what we said there was that if you take two individual mixtures of different strengths, the total amount of water added together, the sum of the water in the mixtures, the original mixtures, the amount of water in the final mixture, and the sum of the acid in the two initial mixtures is the same acid that's in the final mixture. For time problems, what you do is you use this relationship, which is not an additive relationship, but it's a multiplicative arrangement. And basically it says that the distance traveled is equal to the rate, which is the speed, times the amount of time. And you can take this relationship and write it in three different forms. So the distance is rate times time, or the rate, meaning the speed, is how far you go divided by how long it takes you. And the time it takes to go some distance is the distance divided by the rate. So again, you can use that for figuring out, driving somewhere. If I'm, going 60 miles an hour, how long does it take to go 2 hours? How long does it take to go that? If you're going 120 miles at 60 miles an hour, well, you divide the distance, 120 miles, divided by 60 miles per hour, and you'd get 2. The result would be 2, and the units would be hours. So whichever, depends on the problem that you're talking about, what is given. So they can give you problems like this, which I'm not going to put on the test, but I'm going to go through an example here in class. So we have Nancy and Mark commute to work, traveling in opposite directions. Nancy leaves the house at 9 a.m. and travels 35 miles at a rate of 35 miles per hour. Mark leaves at 9:15 a.m. and travels 40 miles per hour. At what time will they be 140 miles apart? So there's a few things you've got to do here. Is you've got to reflect the fact that they leave at different times. So what I'm going to do is I'm going to use the t variable to represent time, but I'm going to use the subscript n to say the time that Nancy's traveling. And the time that Mark is traveling is t sub m. And what we can say is in terms of, and these are in hours, so you have to say what kind of units they are, so they're hours. So who's going to be, looking at the problem, who is going to be traveling for a longer period of time? Nancy or Mark? Because they're saying at what time, the final time is the same between the two. Who's going to be traveling longer time period? Nancy, because she's leaving earlier, right? Well, the speed, that might affect how far she travels, but just talking about time, she's going to be traveling longer because she leaves 15 minutes early. Because they're asking at what time will they be this, so the final time is the same time. Yeah, exactly. Okay, so the time that Nancy's traveling is the time that Mark's traveling plus how much in terms of hours? Yeah. So it's 15 minutes, which is a quarter of an hour. So that's the relationship between the time Nancy travels and the time Mark travels. Now, the distance that Nancy travels, back to this one, distance is rate times time, is going to be the rate that Nancy travels times the time that Nancy travels. And the rate that Nancy travels is 35. And if I use hours, I'm going to leave the units off here. And we'll do, as long as we do miles and hours and we're consistent, we're okay. So it's going to be 35 times the time she travels. And the distance that Mark travels is going to be the rate that Mark travels times the time that Mark travels. So his rate is 40 miles per hour times the time that Mark travels. And in terms of, if I wanted to look at the total distance traveled, in terms of the distances for each person, what would be the answer in terms of these two variables here, since they're going opposite directions? Is it going to be they're added together, they're subtracted from each other, they're multiplied by each other? Okay, those are the choices. I guess they could be divided, but that doesn't make a lot of sense. So how many people vote for you add the two distances together to get the total distance? Okay. Well, we've already got a majority, so that's correct. Okay, so the total distance is, you know, how far you go from the starting point this way and how much starting point that way. So the total distance traveled is going to be equal to the distance that Nancy travels plus the distance that Mark travels. And that has to be 140. That's miles. So ultimately, you know, what we're working towards is a single equation and a single variable. So what then we could do is you could rewrite this equation, but substitute in those variables. So what you'd end up with is for the distance Nancy travels is 35 times the time that Nancy travels. The distance that Mark travels is the speed he travels times the time Mark travels, and that has to equal 140. Okay, so we're down to we have one equation and two unknowns, but we can then substitute in this final relationship. So the time that Nancy travels is going to be equal to the time that Mark travels plus 0.25. Then we add the second term and then the other side. So now, by using substitution and just kind of working through everything that we know, trying to understand the problem and using the definition of the relationship between distance traveled, the rate, and the time, we've finally ended up with an equation in one variable. Now the question is, how do I get rid of that fraction, or do I get rid of the fraction? This one right here. So, or do we just not worry, but do we just do it in decimal form? Because in previous ones we've had the decimal out here, not inside. You could do that. You'll end up with a fraction, which is okay. Yeah, it's not too bad. What you'd have to do if you wanted to get rid of the fraction, you probably wouldn't get rid of the fraction, you probably just deal with it. But if you wanted to get rid of it, what you do is you multiply everything by 4, and so you would have 35 times, so what we're going to do is multiply by 4. You take 35, you wouldn't multiply 35 times 4, you'd multiply everything that's in the parentheses by 4, and the rest of them you would multiply by 4. So 40 times 4 would be 160, and 140 times 4 would be 560. Okay, So that's how you would get rid of the 0.25, but you don't have to. But since I've already done it, I'm just going to go ahead and do it now. So now I would multiply out 35 times both of these terms to get rid of the parentheses. So I'd have 35 times 4, which is 140. So you'd have 140 times t sub m plus 35. 35 times 1 plus 160 times t sub n is equal to 560. And then you combine like terms. So you get 140 plus 160, which would be 300. You would add negative 35 to both sides to isolate the variable term. So you have 300 times t sub m is equal to 560 minus 35, which is 525. And then you would divide both sides by 300. Something's wrong. Seems wrong. Maybe not. We'll find out. Yep. So you get the time that Mark travels is 525 divided by 300, which is one. Oh, it is right. Okay. So it's 1.75 hours. And so the question was, what time will they be that distance apart? So you could go back, since we know Mark's time is going to be an hour and 45 minutes, and he starts at 9:15. You add an hour and 45 minutes to 9:15, and you get the answer, 11 hours. The time that Nancy's traveling is going to be 1.75 plus 0.25, which is 2. So she leaves at 9. 2 hours added on to 9 is 11 also. So that's kind of a way you could check your answer to make sure it makes sense. But ultimately what we did was we said the total time was the sum of the individual time. Well, the total time is the same for both of them. No, that's not true. The final time where the end point is the same. But we reflected that Nancy left earlier by this relationship. We were able to use the given rates to write the distances traveled in terms of that rate times the times. And we said the total distance was the sum of the two distances. And as a result of all that stuff, we were able to come up with a single equation and a single unknown, and then we were able to solve for it. And then we looked to see, what they were actually asking for. And the actual thing they were asking for was not how long they were traveling, but at what time did they reach a point where the total distance apart was the amount specified in the problem. So there's your homework problems for section 2. So there's a fair number, compared to some other sections, there's a fair number of problems, and that's just because the only way you can get good at these problems is just to do them. I'm not going to spend a huge amount of time going over the problems. You'll do them. I'll include one of each kind that I'm going to have on the test. So there's probably a problem involving adding things together, like the airplane problem or the whatever the other one was. There's a couple of mixture problems. There's a couple of interest rate problems, and there's a couple of time. Probably these last two here are ones involving time. So make sure you don't wait till the last minute to do those homework problems, because it's going to take you more than your average homework assignment. So this will be due next Tuesday for the test. Okay, the next thing we're talking about is ratios and proportions, and I can't remember whether this is section 7.3 or 7.4. We skip a section in the interest of not having enough time to do everything. So let me see if I can find what chapter this is. Okay, so we're going to skip section 4. So this is section 3. So we'll go through this, the math, and then we'll do a fair number of examples. And we actually talked about this, as you'll see on the next page. We talked about this last semester. But in terms of words, when they talk about a ratio, it's pretty much ultimately it ends up being a quotient, but you can represent it linguistically here by saying quantity A to quantity B. 5 to 1, 5 cups of flour to 1 cup of water, something like that. That wouldn't do very well though. You could show that as a ratio, 5 cups of flour over 1 cup of water. So you know, something like cooking is where you see ratios a lot, or chemistry is cooking, or cooking is chemistry. And you can also show it by these this colon. That's done more in things like, I would think, like odds for gambling, but you won't see that as much. And it says when ratios are used in when comparing units of measure, the units should be the same. So if you're, if you look at the problem and something is given in cups and teaspoons, you've got to convert either cups to teaspoons or teaspoons to cups. You can't just blindly use the numbers without thinking about units. And the ratios are rational numbers, which is rational numbers have to be the quotient of 2 integers. So we're never going to have an irrational number. We're not going to have pi, even though you could use these numbers to make pi, but not pi as in 3.14, but in terms of pi as in something you can eat. So that's what rational numbers are like quotients. So there's a relation, there's a commonality. Now, chapter 6, which is what we did last semester, we talked about the cross product test for the equality of rational numbers. And so these were 2 rational numbers. A, B, C, and D are integers. And B and D have to not be 0, because if they were 0, then you'd have an undefined result. And so what they're saying is that for these 2 ratios to be equal, the cross product, the numerator times the denominator from one side to the other, is equal to the opposite. So we get A times D is equal to B times C. So that was in chapter 6, we were talking about the equality of rational numbers. In chapter 7, we're talking about proportions or ratios. And so it's basically the same rule. It's just in chapter 7, we're talking about ratios, which are rational numbers. So it's basically the same thing. So in chapter 7, they have this definition. If these 2 ratios are equal, if the cross products are equal, then the original ratios are the same. And that's pretty much it for the math, okay? So you just have to remember sometimes to solve these problems, it's a matter of taking the cross product and then solving for the unknown variable, whichever one that is. One thing we talk about is this definition. Let's just mention this definition. A proportion is a statement that says 2 ratios are equal. So let's go back to so this is a proportion, as long as this is true. So if this is a true equality that's represented as 1 ratio equals another ratio, this is called a proportion. But you don't have to. We don't worry about definitions. So that's just so that you have seen that. Now, how do you manipulate that besides just taking? There's other ways of getting the answer without having to just use the cross product. Because ultimately, if you use the cross product, then you have this extra step. And I think I talked about this the other day. Basically, when you have 2 ratios or a proportion, that you can move things from one side to the other. We just talked about this because we were talking about moving a number from one side of the equal sign to the other. And if you have addition or subtraction, you can just move a number from one side to the other and change the sign. In the case of proportions, you can move a number from one side to the other, but when you move it, you have to take something from the numerator on one side and move it to the denominator on the other. Or you can take it from the denominator on one side and move it to the numerator on the other. So you can just shift these things around depending upon what is the unknown in the problem. So what I could do is if I wanted to solve for A, you know, the long way of doing this is the long way, is you would cross multiply them. So you'd say A times D is equal to B times C. And then you say, okay, to solve for A, I'm going to divide both sides by D. And so this becomes 1. D divided by D is 1, so you get A is equal to B times C divided by D. Okay, that would be the long way. The short way is just to take the original proportion and isolate the variable you're trying to solve for by taking the quantity in the denominator on this side and moving it to the numerator on the other side. So all I'm doing is, what I did was I had my original ratio and I just moved that direction. So I saved myself having a step. Yes? A times, oh, I'm sorry, you're right. Yeah, I don't know why I wrote C. It's B. Thank you. So I'm moving B up here because it's originally down there. Just move it up. I mean, you can still do it that way if you like, but pardon me? Basically, I mean, I'm just saving a step by moving it. I find it more, it's a lot faster to do it the way I'm doing it. Yeah, you just do it mentally. So if I wanted to solve for C, I'd say, okay, I need C by itself. So what I would do is I'd say, okay, I'm going to put C by itself. And to get it, I'm going to move D from the denominator to the numerator. So you just get A times, I can't think right here. So you just get A times D divided by C. Okay, let's try this again. Okay, so what we're doing is we're solving for C. So I'm going to move D up here. So there's B. I forget. There we go. Okay. So it's just a way of solving proportions without having to cross multiply and then divide. It saves you basically 2 steps. Now the tricky part is if you have something like this. So how do you solve for the variables? Well, the way you do that is this is not a ratio. You've got a ratio plus a number. But what we want to do is we want to create a ratio, a complete ratio, so then we could use that philosophy. So what you do is you always want to combine 2 fractions into one fraction and make it into one fraction, and then you can just treat it as ratios. So what you would do is you take the second term in this expression and you would rewrite it as D divided by D. So you get a common denominator. So when you add these 2 together now, you add the numerators together with the common denominator. So now we have this result. You have A over B is equal to C plus D over D. At this point, to solve for A would be easy because what I would do is I would say, okay, I'm solving for A, so I'd write A. I'm going to move B from the denominator to the numerator, and I've just got to remember that I've got to multiply it by the entire numerator. If I wanted to solve for B, what I would do there is I'd say, okay, to get B, to solve for B, I need it in the numerator. So I would say I'm going to move this to the numerator. So I'm going to move that over here. That means everything is, so what I'm thinking of doing here, let me just explain. What I want is, what I'm doing, I'm kind of doing in a shortcut, is this kind of intermediate step. So I have A is equal to B times C plus D over D. So I've moved this to the numerator, and then I would then isolate the B term. So I'd need D to go to this side. So I'd have, sorry, let me fix that. So I put B by itself now on the left-hand side, because I always like to solve things on the left-hand side. I take the D term, move that from the denominator to the numerator, and take this part and move it from the numerator to the denominator. And that would be my final answer. But I wouldn't go to all that trouble. All I would do is I'd say, I'm going to move this up here. So well, actually, I'm going to move this up here. So B comes to the numerator where it needs to be to solve it. And this comes down there, and that goes up there. So I'm just moving things around. I'm moving B up to the numerator so I can solve for it. And to solve for B, I have to move all the other terms to the other side. So this goes from the numerator to the denominator. This goes from the denominator to the numerator. And so I would do it all entirely in my head. And I would just say, okay, move B up here. That means I have A. And when I move this from the denominator, it comes to the numerator. And I take this and I move it to the denominator. And that's my answer. Okay. I mean, even if you did it the old way, you'd still have to combine these two to solve for A. Well, I guess you could just multiply everything by B, but then you'd have a fraction plus a number. So it's always better in this form, anyway, or this form right here. So you just have to get used to playing around with them until you get comfortable with it. Now, to solve for C or D is not quite so easily. What you would have to do from this equation is, at that point you almost have to cross multiply and then do it the long way. But okay, so let's do a couple of simple problems first. Determine the ratio and write in lowest terms. So the ratio in this case is we have A to B. So the equivalent would be, this is A to B. The equivalent mathematical expression would be A divided by B. So you take the written expression and convert it into a mathematical expression and then plug your numbers in. So you'd have 600 people for A would represent the A part of the statement, and 500 people would represent the denominator. You can see the units cancel out. And if I divide the numerator and the denominator by 100, I can simplify it down to 5/6. So that's the ratio is 5/6. And ratios typically, in their most useful form, do not have units because they have the same units in the numerator and the denominator. Okay, here's 288 inches to 12 feet. So again, this would be A to B, which is the same as A divided by B. So we have 288 inches divided by 12 feet. Now, in this case, because this is a conversion factor, you could, if you converted 12 feet to inches, you get 288 inches and you'd get 1. So when you have a result that's just 1 with with units rather than a non-1 without units, it's kind of like a conversion factor. So what I would do here is I would simplify 288 divided by 12. So you just take a calculator. It might just come out to be a whole number, which would, oh, this actually is not a conversion thing. Okay, sorry. So it's not, it's just saying scale this to that. And I realized that when I divided by 288 by 12 inches per foot, and I got 24, and they weren't the same number. So what we would do in this case is we would convert inches to feet. So because they're the wrong units, they're not matching up as far as units are concerned, the first thing you would do is you would take 288 inches and you would multiply by 1 over 12 inches, and so this is to convert inches to feet, or I could convert feet to inches. So to convert inches to feet, I divide by 12. You see the inches cancel out, and I divide 288 by 12, and I get 24 feet. So my original ratio here is 24 feet divided by 12 feet, and that gives me 2, a ratio of 2. So it could be something like you're building a rectangular house and you want one side to be twice as long as the other. For some reason they gave you one side in inches and the other side in feet. I don't know why they would do that. But okay, the next bunch of problems just asks you whether proportions are true or false, and we do use the cross multiplication test for that. So rather than trying to simplify these down, that would be the other way of doing it, is you could simplify these two fractions or two ratios down to their simplest terms. But what they're looking for you to do is just to cross multiply, and if the cross multiplications are not equal to each other, then the original proportion is false. If they're equal to each other, then the proportion is true. So we'll say to check whether proportion is true, cross multiply. So you take 5 times 56, and you would ask the question, I'm going to put a little question mark because we don't know if it's equal, because we don't know if this is true or false. So if we take 5 times 56, which is 280, is that equal to 8 times 35, which it is. So we can say, so since the cross multiplication was true, meaning equal, the original proportion is true. So I think we have another example here. No, actually we don't. But if we multiplied these together and they didn't equal each other, then we would say, we'd get to this point and they're not equal to each other, and we'd say, so since the cross multiplication was false, meaning not equal to the original, I messed up a word here. So since the cross multiplication was true, that should be the original proportional is true. So if it's not equal to each other, if the cross multiplied values are not equal to each other, then the original proportion is false. That's how you would write that. Now to solve this problem, to solve for the unknown variable, you could cross multiply, but I'm going to use my technique that I just talked about, and I'm going to solve for x. And what I would do is I'd say, to solve for x, I need to move this to the other side. Because it's a ratio, I can just move it directly, so I'd get 49 times 8 divided by 56. And then I can just do that in my calculator. So 49 times 8 divided by 56 is 7. And so that's the answer. The other way, the long way, you'd have 56x equals 8 times 49. 56x equals 8 times 49 is 392. Then you divide both sides by 56. and you get x equals 7. So by using my approach, by taking the original proportion and just solving for x by moving the term that's in the denominator to the numerator on the opposite side, I miss having to do all this stuff, which I don't miss too much, and then I get the final answer like that. So that's a couple problems like that you got to do. Now in this case, it's not quite as simple. In this, you probably would just cross multiply. So when it's not just a simple proportion, in this case I am going to cross multiply. So to solve for x, I take the numerator on one side, multiply with the denominator on the other side, and do the same thing for the other. And I purposely put the constant part, the denominator, in the front. So you might have been tempted to say this times that, but I just switched them, this times that, just so it looks more as a normal distributive type relationship. And then you can first step is to get rid of any fractions or decimals, which we don't have. The second step is to multiply out the terms so that you don't have any parentheses. So we get that. And then we would solve for the variable term by adding the additive inverse of the variable term that's on the other side. We do the same thing here with the -6. So I'm taking the additive inverse of 6, which is -6. I'm adding it to both sides. Then I do the math. Everything half the stuff should cancel out. 18 minus 14 is 4. This goes to 0. This goes to 0. This goes to -27. And then you divide by 4. So you get x is equal to -27/4. And one word of warning, on the tests, I don't make any special effort to make it to be an integer. So if you get a fraction, don't worry that much. Just make sure you did the correct procedure. Doesn't necessarily mean you made a mistake. In this case, I'm not plugging back into my original equation because I'm lazy. Once you'd end up with a lot of fractions, so I'm decided not to do that. Okay. Now, linear equations that have no y-intercept, we call those a special case, and we call it direct variation. So when you have a relationship between the x variable and the y variable, the independent variable and the dependent variable is just some factor k. That's called a direct variation. And there are a lot of cases of direct variation. I gave you that example. I think I'll show you my physics example, which I got in here. One of the most important relationships is the force the spring gives versus how much you stretch the spring. So this is the unstretched length. And if I say stretch the spring 1 unit, I would measure a force. So I've actually got some scales in here, which are also in themselves springs, but that's okay. Oh, I got to close that thing. So if I took this spring and I attached this scale and I stretched it, say x units, like that, I'm moving it so that the thing moves to the first increment. If I stretched the spring twice as much, then if I was actually measuring the length of this stretched spring, that the spring would be stretched twice as long here as it would be there. So the force for twice the length to get twice the force. If I did 3 times, then it would be 3 times the length. It would go way out here, except that my arm's not long enough. Okay. So that's a very useful relationship. It relates springs to the characteristics of the spring to the relationship between the force of this wants to pull this thing back together, and the displacement. And so there's one of the consequences of that is that if I hang a mass from the spring like this, and I look at the movement of this object as it bounces up and down, if I actually looked at where this thing was displaced as a function of time, it would look like a sine wave. And that's a consequence. A sine wave looks like this, okay? Like a wave you'd see in the ocean. And that's a direct consequence of the relationship between the stretching of the spring and the restoring force. Because it's always, if I do it exactly right, it doesn't move. This is called equilibrium. But if I displace this from equilibrium, what it'll do is it will oscillate around that equilibrium position. It'll go the same distance above and below that. And where this thing is as a function of time is related to a sine wave. So anyway, that's one example of a linear relationship or direct proportion. And the ratio of y to x, this constant k, is some proportionality constant, which turns out in the case of a spring to be what we would call the spring constant. So even though you might think, I've been doing this since 7th grade, that seems like, does anything really behave in that manner? And the answer is yes. There are a lot of things that behave in a linear relationship. And the other case is an inverse relationship. So instead of k times x, it's k divided by x. So when we had, in the previous case for direct variation, the ratio of y and x was equal to k. In the case of inverse relationship, the product of the two is equal to a constant. So there are cases, what's an example of that, where you have an inverse relationship? Well, there is, we were talking about the ideal gas law the other day, for you chemistry guys. Ideal gas law. The ideal gas law says P, pressure times volume, is equal to the number of moles times universal gas constant times T. Well, at constant temperature, so let's say you maintain something at a constant temperature, P times V is equal to a constant, ends up being a constant. Constant T, N equals a constant, meaning I have the same amount of gas. So you have gas at constant temperature with the number of moles, PV is equal to a constant. Well, that's exactly what this is. Or you'd have P is equal to some constant divided by V. So that's that way to look at it. So, the case of constant temperature ideal gas, that is an inverse relationship between pressure and volume. And I'm trying to think of it. There's other things. Has to do with forces or energy between two objects. Like the gravitational energy between two objects is inversely proportional to the distance. Okay, so here's some problems. Let's do some word problems. And I usually include a couple of word problems involving ratios on the test. So it says, if 12 ringtones cost $30, how much do 8 ringtones cost? The answer is 20, but how do we get to that? So, this is a proportion, cost to number of items, cost to number of items, and it's the same. We're not getting any discount for for higher purchases of ringtones. So one way of doing this would be to calculate the cost per ringtone. And then once you have the cost per ringtone, you multiply by any number of ringtones and you get the final answer. But the easy way to do this is to set it up as a proportion. So don't be tempted to necessarily do it cost cost per ringtone. The way you would do it is you would have some kind of ratio. A over B is equal to C over D, where these ratios are either the same quantity, the same variable, ringtones. But you could also end up doing it in terms of the one condition to the same condition, but as long as you're consistent with the that the numerator is associated with one condition and the denominator is associated with another condition. So let me explain what that means. I'm going to show it both ways and show you get the same answer. So if you could set it up as 12 ringtones is to $30 as another proportion. And in this case, you want to have ringtones on the top and you want to have dollars on the bottom. So those have to be consistent. So we just go back to the problem. The first ratio was 12 ringtones to $30. Then it's 8 ringtones to X dollars. So the thing they're asking for is how much does 8 ringtones cost? So what we would do is just, again, since these are just simple ratios, we can move this thing that we're trying to solve for from the denominator over here to the numerator over there, to the left, from the right to the left, and then we can take the other two quantities that are over here and move them to the other side. Well, this one is in the numerator, so it has to go to the denominator, and I'm grouping it with the other ringtone. So this one comes down, this one goes up, and then I can multiply it out. Notice the ringtones cancel out as far as the units, and the rest we can just do in our calculator. So we take 8 times 30 divided by 12, and we get $20. And it makes sense because buying less ringtones should cost less money, and it is less money. Okay, so that's using that particular proportion. The other example of a proportion, let me just put this up here, is you could say, instead of doing, these are matched together, these are grouped together. The other way to do it would be 12 ringtones to 8 ringtones. So I'm using the ratio is ringtones instead of ringtones to dollars. And so then I have another proportion over here, and I just have to match up the correct dollars with the correct ringtones. So 12 ringtones are in the numerator, therefore the $30 has to be in the numerator. And the unknown number of dollars has to be in the denominator because that's the unknown cost for 8 ringtones. So now I can just shift things around again. I'm going to solve for the unknown. So I'm going to take that from the denominator and move it to the numerator. I'm going to leave my $30 over here. So when I move 12 to the other side, it has to go to the denominator. And the 8, which is in the denominator, has to go to the numerator. And at that point, you see we're basically at the same equation. We've just got these switched. So if you solve for it, you get $20. So either approaching it either way is fine. You just have to be consistent about that either the like quantities, meaning dollars or ringtones, are either both in the numerator or both in the denominator. When you deal with the putting the similar type of things together and you create a ratio, you just got to be able to make sure that the numbers over here correspond with the correct values. So I don't put $30 in the denominator because the $30 goes with the 12 ringtones. Now the third way I could do it is I could calculate the cost per ringtone, which would be 30 divided by 12. And then I could take that number and multiply by 8 ringtones. Cost per ringtone times ringtones gives me cost. And I get the same answer, but I just, oh, and it's time to quit. Boy, yep, thank you for shuffling your papers there because I would have not noticed that. Okay, let me assign the homework from this section. So before we,
You only really want to do the by unit thing if you're going to be doing multiple problems that would be able to use that.
that would be the only time that you would use it. Anyway, a lot of problems again, but they're all pretty simple. So those are also due next Tuesday. But we'll come back and we'll do some more on Thursday. We'll do a spring problem. We'll probably do I forget what the other ones are. And the last section that we cover in Chapter 7 has to do with exponents, which we did a little bit in first semester, but we're going to do a little bit more here. Okay.
You wouldn't be interested in any